Hi, I'm Dr. Incognito. In this video, we're going to study the limit comparison test. The limit comparison test. The test goes like this. Suppose we're given an infinite series of positive terms. We are going to create a series that is similar to the original, also having positive terms, whose behavior is known. It's known to either converge or diverge. Something like a p-series or a geometric series. So the summation of Bn is going to be a series that we have knowledge of. Then we consider the following limit. The limit as n goes to infinity of an over bn. And we suppose that that limit is L. Then the conclusion for the limit comparison test is as follows. If L is any positive number, then both series, the summation of an and the summation of bn, will do the same thing. Then both series converge or both diverge. So the ANs, the summation of the ANs, will do whatever the summation of the BNs do. So it's important that we know what the summation of the BNs do. So as an example, let's look at the summation n equals 1 to infinity of n plus 1 over n cubed. The fractions in this example certainly remind us of the summation of n over n cubed, which of course is the summation of 1 over n squared. So our bn's are going to be 1 over n squared. This is a p-series. P is equal to 2. It's greater than 1. And so therefore, the p-series converges. So now we'll calculate this limit, and we will see if we get a positive number. So the limit, as n goes to infinity, of an over bn, is equal to the limit as n goes to infinity of n plus 1 over n cubed times n squared over 1. When we calculate the fraction an over bn, we write it as an times the reciprocal of bn. Bn is 1 over n squared, so its reciprocal is n squared over 1. So now this limit becomes the limit of n cubed plus n squared over n cubed. We have two polynomials here that have the same power, the same degree. They're both third degree polynomials, so the limit at infinity can be calculated as the ratio of the lead coefficients. So 1n cubed over 1n cubed, that's 1 over 1. So the limit is 1. That's our value of L. That's clearly between 0 and infinity. Since 1 is bigger than 0 and less than infinity, both series have the same behavior. The summation of 1 over n squared was convergent, so both series converge. So the series that we were given here is a convergent series. As one last comment, this fraction is very, very similar to the fraction n over n cubed, which simplifies to 1 over n squared. So we might try to make a direct comparison between these two fractions, but unfortunately that direct comparison will go in the wrong direction. What I mean is, these fractions are slightly larger than 1 over n squared because of the plus 1, and so the direct comparison test would not give us a conclusion. We would have a summation of fractions which are larger than the summation of fractions in a convergent series, so we don't get a conclusion from direct comparison. So the limit comparison will help us out. Another example, let's consider the summation n equals 1 to infinity of 3n squared plus n divided by the square root of 4n to the 5th plus 2. So that's a pretty complicated looking fraction there. I would not want to have to make a direct comparison involving these fractions. But what I can do is I can say this reminds me of, on the top, n squared, and on the bottom, the square root of n to the 5th. Just focusing on the highest powers that we see. So this is n squared over n to the 5 halves, and that simplifies to 1 over n to the 1 half. So I'm going to try a limit comparison with the summation of 1 over n to the 1 half, n equals 1 to infinity, 1 over n to the 1 half. This is a p-series. P is equal to 1 half. The rule there is if the p value is less than or equal to 1, then the series diverges. So now let's compute the value of L. Let's calculate this limit and determine the value of L. If L is any positive number, then both series will do the same thing. They'll both diverge. So let's see. The limit as n goes to infinity of an over bn is equal to the limit as n goes to infinity of 3n squared plus n over the square root of 4n to the 5th plus 2 times the reciprocal of bn. I'm going to write it as the square root of n over 1, n to the 1 half. Let's put it in the format of the square root of n. So to calculate this limit, I'm going to put everything under a square root. So I'm going to write 3n squared plus n as the square root of 3n squared plus n quantity squared. And then we have times the square root of n and divided by the square root of 4n to the 5th plus 2. So now using properties of square roots, I can replace these three separate square roots by one big one. So this is equal to the limit as n goes to infinity of the square root of the big quantity 3n squared plus n, quantity squared, times n divided by 4n to the 5th plus 2. So the answer is going to be the square root of, what's my limit here? If we were to square this out and then multiply by n, because there's an n squared there, and n squared squared is n to the 5th, n to the 4th, excuse me, then times n will give us n to the 5th. We will have a 5th degree polynomial on the top and a 5th degree polynomial on the bottom. So the limit inside the square root is the ratio of the lead coefficients. The lead coefficient on the bottom is obviously 4. And on the top, the lead coefficient, what will that be? When we square this one, we'll get 9n to the 4th times that n is going to be 9n to the 5th. So the lead coefficient on the top is going to be 9. So the square root of 9/4. So the L value is 3 over 2. So the conclusion here is, since 3 over 2 is between 0 and infinity, both series do the same thing. So both series, we're comparing with a divergent series, so both series diverge. The series in the problem, this complicated beast, that series diverges because it basically behaves like this p-series. In fact, what this 3 halves is telling us is that it's behaving like 3 halves times this p-series. You see, when an over bn approaches L, that's basically saying that the an's are approximately the constant L times the bn's. And since the constant L is a positive number, if the summation of the bn's converges, then multiplying it by a positive number will still converge, and if the summation of the bn's diverges, then multiplying it by a positive number, it will still diverge. So that's why this fraction is considered, and we want L to be any positive number, because that way a positive number times a series doesn't change the behavior of the series. So both series will have the same behavior. Okay, I hope you found this discussion of the limit comparison test to be helpful.